Hello everyone, I'm Dhanawansa from Sri Lanka Institute of Information Technology, and I will be presenting the paper titled An Investigation of the Effects of Kernel Tuning on the Performance of Convolutional Neural Network Architectures, a case study of non-instructive load monitoring applications. Authored by myself, G.M. Herath, C.J. Angammana, T.D. Thilakanayake, and M.H. Liyanage. The increase in the global energy consumption over the recent years has created a need for real-time and reliable energy monitoring. Having identified that a significant portion of this energy consumption is domestic, it is crucial that the energy consumption is monitored such that consumers can minimize their energy usage. In the past, instructive load monitoring methodologies have been investigated where the appliance-wise energy consumption is measured using low-end metering devices. Here, separate sensors are typically placed close to the relevant appliances, where each sensor measures the energy consumption of the device individually. This implies that this approach of energy monitoring is costly. Also, given that different sensors would have to be used with each appliance, it gives rise to the need for the establishment of communication protocols. With the addition of new devices, the user is burdened in installing new sensors, which reduces the feasibility of this approach and results in a high operational complexity. All these factors highlight the need for an improved method. Therefore, with the introduction of smart meters such that multiple sensors would not have to be used, non-instructive load monitoring methods have taken precedence over instructive load monitoring. Within the discussed NILM approach, the smart meter results in an aggregated energy signal. Therefore, it is necessary to be segregated into the various appliances, which brings us to the concept of energy disaggregation. As shown in this slide, the overall energy signal should be separated to the individual appliances, such as the fridge, dishwasher, and microwave. This approach allows the analysis of each energy signature separately so that the consumer can be given useful feedback on the energy usage of each appliance, allowing them to manage the usage of their appliances effectively. Moving on to the energy disaggregation methodologies that have been used in the past, traditionally, manual feature extraction has been implemented, for example, using spectral domain and Fourier analysis. However, such approaches prove to be time-consuming since the optimal set of features for analysis have to be manually extracted. Furthermore, adapting such a methodology to include new devices would be a complex task. However, with the increased availability of computer resources such as graphical processing units and the increased availability of reliable and well-organized energy datasets, deep learning techniques, which includes convolutional neural networks, recurrent neural networks, and LSTMs, or long short-term memory networks, have been implemented. Furthermore, CNNs have shown a strong capability in automated feature extraction and classification of image data, and also reduce the need for extensive pre-processing. This has led to a surge in the use of CNNs within the NILM domain. Therefore, in our study as well, we propose the use of a 2D convolutional-based disaggregation method. Diving further into the motivation of this research, we understood that the performance of a CNN is governed by the hyperparameter selection, which includes the kernel size, batch size, loss function, and optimizer function, since a CNN functions as a black box. However, the relationship between such parameters and the model performance within the NILM domain has not been investigated. Therefore, this presents a motivation of our research to investigate the effect of various kernel sizes on the performance of the NILM architecture. Therefore, we performed a rigorous experimentation with the aim of proving the generalization capability of kernels to achieve the optimum CNN performance. The proposed CNN architecture for feature extraction and classification is shown in this image. The model consists of 3 parallel convolutional layers, which are then followed by a concatenating layer, 3 convolution layers of kernel sizes of 3, 5, and 7, a max pooling layer, a flattened layer, and a dense layer of 128 neurons. Finally, we incorporate a dense layer containing the number of neurons equal to the number of output bins. Within this study, we investigate the effect of different sized kernels for these mentioned parallel layers. Moving on to the data acquisition and pre-processing stages for this study, we used a benchmark dataset known as RED, or Reference Energy Disaggregation Dataset, for both training and testing purposes. In order to improve the performance, the dataset was subject to a series of pre-processing stages. The dataset was first organized in increasing order of timestamps and checked for the possibility of missing data points. Missing intervals fewer than 5 seconds were forward filled, and those exceeding this limit were removed from the dataset. In order to account for sudden spikes in the data, which is commonly observed in energy datasets, equally spaced sample data was used. Thereafter, the activation windows were extracted using the NILM toolkit and concatenated to create the aggregate energy signals. Afterwards, in order to predict appliance-wise energy consumption, a sequence-to-point classification-based approach was used, resulting in the input window being mapped to a single point on the output window, which is illustrated in this figure. A soft association method was used such that the probabilities of the prediction were assigned to each output, in contrast to a hard association method where only a single output bin is selected. The previously presented CNN architecture was used for the classification process, where we implemented the Adam optimizer, the categorical cross-entropy function, and test and train all our methods over 25 epochs. The mentioned kernel sizes, which includes odd kernels such as 333 and 555, combinations of different sized kernels, which includes 355 and 357, and even kernels such as 222 and 444 were implemented. We define various training and testing protocols, which involves the two appliances, fridge and dishwasher, which show different energy signals, which can be viewed in these figures. In addition, we define two test categories known as seen house and unseen house. In seen house, the data of the same house was used for both training and testing, whereas in the unseen house, the training and testing of the CNN was conducted on data of two different houses. We define a total of 7 protocols as highlighted in the table, incorporating the data of the fridge and dishwasher for both seen and unseen categories. Thereafter, for each protocol, we implemented the defined kernel configurations with the intention of identifying the most optimal kernel combination. In order to compare the performance resulted by the different kernel sizes, we extracted the accuracy and loss of the training and validation data. This image depicts the sample training and validation performance over the 25 training epochs. It is evident that the validation data showcases large variations, which is caused by the different data batches which were used for training and validation. Each data batch consisted of a sequential sliding window with 1 second intervals and random windows with the aim of improving the generalization of the training model. Therefore, in the study, we account for these significant variations and then extract the average validation accuracy. This table presents our extracted results. In general, it was evident that even kernels of 222 and 444 resulted in an optimal performance amongst the tested kernel configurations, which is supported by 4 out of the 7 protocols. Usually, programmers tend to apply odd kernels of 333, for example, whereas our work suggests that even-sized kernels would generate a more optimal performance. Further analyzing the remaining protocols, a marginally improved performance was obtained for the different kernel configurations compared to the even kernels. However, results show that even and similar-sized kernels of 222 and 444 have generated comparable results for these protocols as well. Further analyzing the unseen test protocols, the reduction in the average validation accuracy in comparison to the seen test category, which results in accuracies of approximately 90%, was due to variations in the energy signals of different houses. Additionally, it was evident that houses 2 and 3 contain a similar trend in energy signatures in comparison to houses 1 and 3, which results in a much higher average validation accuracy of approximately 60% for protocols 6 and 7, when compared to protocol 5, which results in an average validation accuracy of only 38%. In future, we hope to expand our work to investigate the effect of the number of filters, batch size, activation function, and optimizer function in order to find the relationship between these parameters and the CNN performance. Also, similar experimentation could be conducted on similar CNN models formulated for other applications in order to further validate our conclusions. Thank you, and please feel free to raise any concerns you may have regarding the presented work.